All right, let's try one of these indeterminate differences. And I guess spoilers, this is an indeterminate difference. So first, let's just check to make sure. So we're doing the limit as x approaches 1 from the right. Our function here is 1 over natural log x minus 1 over x minus 1. X is approaching a number, so we can just try plugging in and see what we get. And in each of these, when we plug 1 in here, we get 1 over natural log 1, but natural log 1 is 0. So that's a c over 0 form. And when we plug 1 into this fraction, we get 1 over 0. Also a c over 0 form. So individually, we can check this. The limit of 1 over natural log x is positive infinity as x approaches 1 from the right. It's a c over 0 form, so you just use a test number to figure out if it's positive infinity or minus infinity. And because we're approaching 1 from the right, natural log is slightly positive then. So this is going to be positive infinity. And then you can also check that the limit of 1 over x minus 1 as x approaches 1 from the right. This is also a c over 0 form, so it's going to be either plus or minus infinity. And if we use a test number, something close to 1 but slightly bigger, we're going to end up with a positive. So this is also positive infinity. And so what we have here is this is an indeterminate infinity minus infinity form. It's our indeterminate difference. All right, so how do we handle this? Well, if it were a, we might be able to write this as a product, but as it stands, it doesn't look like, at least right now, there's anything to factor out. What we do see is that we have two fractions that we're subtracting. And so a lot of times with fractions, our strategy is to just do a common denominator, try to combine them into one fraction. And that's going to be our strategy here. So we're going to try a common denominator. See what that gets us. All right, so let's try it out. We're going to do the limit as x approaches 1 from the right. And what's going to be our common denominator? Well, just multiply these two together. So it'll be natural log x times x minus 1. And in this first fraction, the natural log was already there. So how do I get that x minus 1? Well, I have to put an x minus 1 in the numerator. And then I have my second fraction. It's going to be the same denominator. The x minus 1 was there originally. I put in a natural log x, so I have to put that into the numerator as well. All right. So now with these in common denominator form, I can actually combine them into one fraction. So this is going to be the limit as x approaches 1 from the right of x minus 1 minus natural log x all over natural log x times x minus 1. Get a good multiplication dot there. Sure, why not? All right, so now we've kind of changed our function a little bit. We've rewritten it. So let's see what's going on now. So we plug 1 in, and we get 1 minus 1. So we get 1 minus 1 minus natural log 1. And then we get natural log 1 times 1 minus 1. Well, natural log 1 is 0. 1 minus 1 is 0, so we end up with 0 over 0. All right, well, that doesn't really tell us too much, but it does tell us that we have a fraction here. It's an indeterminate quotient, so we can actually use L'Hopital's rule. So that's what we're going to do. We're going to use L'Hopital's rule, so we put a little h there to indicate what we're doing. And then we apply the derivative to the top of our function and to the bottom of our function here. All right, so let's see what we get. So if we differentiate the terms in the top, derivative of x is 1. Derivative of minus 1 is 0, so we won't write that. And then derivative of minus natural log is minus 1 over x. Okay, not too bad. Well, good thing I really emphasized that product there, because we're going to differentiate the terms in the denominator here, and it's a product. It's natural log x times x minus 1. So we have a product here of two x terms, so we have to use product rule. So if we apply product rule, and you might want to kind of go through the steps to check this out, we're going to end up with 1 over x times x minus 1 plus natural log x. So there's a little bit of product rule right in here. Try it out. All right, so we've applied L'Hopital's rule. Good. And right now I see a lot of fractions stacked on top of fractions. So normally we try to simplify that, see where that gets us. And so I might try multiplying. I want to get rid of this 1 over x. So what could I do? Multiply the top by x. And I can't just do that free of charge. I have to also do that to the denominator then. So I'm going to multiply this whole denominator by x. So when I do that, I get x minus 1 on the top, and then I get an x minus 1 plus x times natural log x on the bottom. And we're doing the limit as x goes to 1 from the right. Okay. Maybe made it a little nicer. I don't know if it did too much. But let's see what happens now. So we have a brand new limit now. We tried simplifying it. Maybe that helped. Let's plug 1 in and see where we are. Well, when we do that, we get 1 minus 1 over 1 minus 1 plus 1 times natural log 1. It's another 0 over 0 form. So really, we have to do L'Hopital's rule again. So we apply it again. So let's differentiate the top here. Derivative is just 1. Now that's good, because now we've kind of gotten the numerator as simple as we can possibly get it. What about the denominator? Well, derivative of x is 1. Derivative of minus 1 is 0. And then we also have another product here. So when we go to differentiate this, we're going to need some product rule. And what do we get? Well, we get plus natural log x plus x times 1 over x. And that's product rule there. All right, so let's simplify this. And there's not too much we need to do, but I have this x times 1 over x. Let's cancel those out. And so x times 1 over x is just going to be 1. And I'll add it to this one here. So we're going to have 2 plus natural log x. And now we have this brand new limit to work with. Let's try plugging in again. We plug 1 in. And we get 1 over 2 plus natural log 1. Natural log of 1 is 0. So we end up with 1/2. And what we're doing here, finally, is that we're just doing our direct evaluation. We're just doing our direct evaluation, and we can do that because this function is continuous. We're not getting division by 0, and it's natural log function, which is continuous at 1, and then it's just a fraction and some addition in the denominator. We're not getting division by 0. So this is a continuous function. No division by 0. And so this is another one of our strategies if we have these infinity minus infinity forms is, well, if you have a fraction, maybe common denominator works. And you're able to try to take this subtraction that's going on. And what did we do? Well, we converted it into a fraction, into a single quotient here. And that quotient was the 0 over 0 form. And then we fall into the groove of L'Hopital's rule, simplify, get a brand new limit, check to see what's going on, Nope, still another indeterminate form, so apply the rule again. 0 over 0 form, we can do L'Hopital's rule again. Get a brand new limit, maybe simplify a little bit, and then check. And here we finally got an actual numerical answer. And that's it. That's our answer right there. All right, so just a little bit more fun there for L'Hopital's rule. All right, so we'll look at some more indeterminate forms coming on up.